In the year 1900, a German physicist named Max Planck made a discovery so radical that it would shatter everything we thought we knew about reality itself. He wasn't trying to revolutionize science, he was simply attempting to solve what seemed like a straightforward problem about how hot objects glow. But what he uncovered would force humanity to confront a terrifying truth. The universe doesn't work the way our eyes tell us it does. Energy doesn't flow like water from a tap. Matter doesn't behave like tiny billiard balls. Instead, reality operates according to rules so bizarre that even Planck himself refused to believe what his own mathematics was telling him. This is the story of how one man's reluctant hypothesis cracked open a door to a quantum realm where particles exist in multiple places simultaneously, where the act of observation changes reality, and where the fundamental building blocks of existence dance to rhythms that defy human intuition. If you're ready to discover how Planck's desperate attempt to fix a broken equation accidentally revealed the secret architecture of the cosmos, then prepare yourself for a journey that will forever change how you see the world around you. The year was 1900, and physics was supposedly nearing completion. Scientists believed they had mapped nearly every corner of the natural world. Isaac Newton's laws explained motion with mathematical precision. James Clerk Maxwell's equations described electricity and magnetism with elegant beauty. The universe appeared to be a vast clockwork mechanism where every cause produced predictable effects. But hiding in the shadows of this confident worldview lurked a problem that would soon expose the shocking inadequacy of classical physics. The problem centered on something called blackbody radiation. Picture a piece of metal heating up in a furnace. As the temperature rises, the metal begins to glow, first red, then orange, then white hot. This thermal radiation follows specific patterns that scientists could measure with remarkable accuracy. Every object at a given temperature emits electromagnetic radiation in a characteristic spectrum. The hotter the object, the more energy it radiates, and the bluer the peak wavelength becomes. This relationship seemed straightforward enough, but when physicists tried to predict the exact amount of energy radiated at each frequency using classical physics, they encountered a mathematical catastrophe. According to the established laws of thermodynamics and electromagnetic theory, the total energy radiated by any heated object should be infinite. This prediction, known as the ultraviolet catastrophe, suggested that every warm object in the universe should be pumping out unlimited amounts of high-frequency radiation. Obviously, this didn't happen in reality. Your coffee mug doesn't emit deadly gamma rays. Your body doesn't glow like a nuclear reactor. Something was fundamentally wrong with classical physics, but no one knew what. Scientists had tried everything to resolve this contradiction. They developed increasingly sophisticated mathematical approaches, refined their experimental techniques, and questioned their basic assumptions. Yet the ultraviolet catastrophe persisted like a mathematical monster that refused to be slain. The discrepancy between theory and experiment wasn't subtle. It was spectacular and complete. Classical physics didn't just give the wrong answer, it gave an impossible answer that violated the basic principles of energy conservation. This is where Max Planck entered the story, driven not by revolutionary ambition but by scientific desperation. Planck was a conservative physicist who deeply respected classical theory. He had no intention of overthrowing the established order. Instead, he hoped to find a way to modify existing equations just enough to make them match experimental observations. What he discovered would prove far more revolutionary than anything he could have imagined. Working with the mathematical precision that had made German physics legendary, Planck began searching for a formula that could accurately describe blackbody radiation. He tried various approaches, tweaking equations and adjusting parameters. Nothing worked. Classical physics stubbornly continued to predict infinite energy output. Faced with this mathematical dead end, Planck made what he later called an act of desperation. He introduced a radical assumption that violated every principle of classical physics. Planck proposed that energy could only be absorbed or emitted in discrete packets rather than continuous amounts. Instead of flowing smoothly like water, energy came in separate chunks like grains of sand. The size of each energy packet was proportional to the frequency of the associated electromagnetic wave. Higher frequency radiation came in larger energy packets, while lower frequency radiation came in smaller ones. The proportionality constant linking energy to frequency became known as Planck's constant, represented by the letter h. This assumption seemed absurd from the perspective of classical physics. Energy had always been considered infinitely divisible. You could have half as much energy, or a quarter as much, or any fraction imaginable. The idea that energy existed only in specific discrete amounts was like suggesting that water could only be poured in predetermined cup sizes. It violated fundamental assumptions about the continuous nature of physical quantities that had guided scientific thinking for centuries. Yet, when Planck applied this bizarre assumption to his black-body radiation calculations, something remarkable happened. The mathematics worked perfectly. His formula accurately predicted the experimental observations across all frequencies and temperatures. The ultraviolet catastrophe vanished because high-frequency radiation required such large energy packets that thermal energy couldn't create them efficiently. Only radiation with moderate energy requirements could be easily produced, exactly matching what experiments revealed. The success of Planck's formula was undeniable, but its implications terrified him. If energy truly came in discrete packets, then the entire edifice of classical physics needed to be rebuilt from the ground up. Planck initially hoped that his quantization assumption was merely a mathematical trick, a convenient fiction that somehow produced the right answer without reflecting physical reality. He spent years trying to find a way to derive his successful formula using purely classical reasoning. He never succeeded. The energy packets that Planck reluctantly introduced became known as quanta, from the Latin word meaning how much. Each quantum represented the smallest possible amount of energy that could be associated with electromagnetic radiation of a given frequency. The relationship between energy and frequency was elegantly simple, yet profoundly revolutionary. Energy equals frequency multiplied by Planck's constant. This deceptively simple equation, E equals h times nu, would become one of the most important relationships in all of physics. Planck's constant itself proved to be an entirely new fundamental constant of nature. Its value, approximately 6.626 times 10 to the negative 34 joule seconds, is incredibly small by everyday standards. This tiny magnitude explains why quantum effects remain hidden in our macroscopic world. The energy packets associated with visible light are so minuscule that we cannot detect their discrete nature directly. Light appears continuous to our senses, just as a beach appears smooth despite being composed of individual grains of sand. The smallness of Planck's constant also reveals why classical physics worked so well for centuries. When dealing with large objects and high energies, the granular nature of energy becomes negligible. A baseball flying through the air contains so many energy quanta that its motion appears perfectly smooth and continuous. Only when examining individual atoms, electrons, or photons does the discrete structure of energy become apparent. But Planck's reluctance to embrace the full implications of his discovery demonstrates just how radical the quantum concept truly was. Even its creator struggled to accept what his mathematics revealed. The idea that nature operates in discrete jumps rather than smooth transitions challenged basic intuitions about how the world should work. Yet, experimental evidence increasingly supported the quantum hypothesis, forcing physicists to confront an uncomfortable truth about the fundamental nature of reality. The concept of energy quantization opened a door to understanding phenomena that classical physics could never explain. It provided the first glimpse into a microscopic realm where particles behave like waves, where probability replaces certainty, and where the act of observation can influence the outcome of measurements. Planck's desperate mathematical fix had accidentally revealed the quantum fabric underlying all existence. Within 5 years of Planck's breakthrough, Albert Einstein would extend the quantum hypothesis to explain another puzzling phenomenon called the photoelectric effect. Einstein recognized that if energy is quantized, then light itself must consist of discrete particles called photons. This insight earned Einstein the Nobel Prize and demonstrated that Planck's quantum concept had implications far beyond blackbody radiation. The photoelectric effect occurs when light strikes a metal surface and ejects electrons. Classical physics predicted that brighter light should eject electrons with more energy, regardless of the light's color or frequency. Instead, experiments revealed that only light above a certain frequency could eject electrons at all. Increasing the brightness increased the number of ejected electrons, but not their individual energies. This behavior made perfect sense if light consisted of photons with energies determined by Planck's relationship. Einstein's explanation of the photoelectric effect provided compelling evidence that electromagnetic radiation truly does come in discrete packets. Light wasn't just quantized in its interaction with matter, as Planck had suggested. Light itself consisted of quantum particles that could transfer their energy in all-or-nothing transactions with electrons. This revelation transformed our understanding of the nature of light and established the quantum hypothesis as a fundamental principle rather than a mathematical convenience. The success of quantum theory in explaining both blackbody radiation and the photoelectric effect marked the beginning of a scientific revolution that would completely transform our understanding of reality. Yet these early triumphs were merely the first steps in a journey toward discoveries that would prove even more strange and counterintuitive than Planck's original energy quantization. The implications of Einstein's photon concept sent shockwaves through the scientific community that reverberated far beyond the confines of university laboratories. If light could behave as discrete particles, what did this mean for everything else? The answer would emerge from an unlikely source, a young French aristocrat named Louis de Broglie who dared to ask the most audacious question in the history of physics. If waves could act like particles, could particles act like waves? In 1924, de Broglie submitted a doctoral dissertation that would forever alter humanity's perception of matter itself. His proposal seemed to border on scientific heresy. Every electron, every proton, every atom in your body should exhibit wave-like properties under the right circumstances. The wavelength of these matter waves would be inversely proportional to their momentum, following a relationship that incorporated Planck's constant. Massive objects like baseballs and automobiles would have wavelengths so incredibly small that their wave nature could never be detected. But electrons and other subatomic particles might reveal their hidden wave characteristics through carefully designed experiments. De Broglie's professors at the Sorbonne weren't sure what to make of his radical thesis. The idea that solid matter could simultaneously possess wave properties challenged centuries of accumulated wisdom about the nature of physical objects. They sent his dissertation to Einstein for evaluation. Einstein's response was immediate and enthusiastic. Not only did the mathematics work, but the concept provided elegant explanations for phenomena that had puzzled physicists for years. The experimental validation of de Broglie's matter waves came just 3 years later through the work of Clinton Davison and Lester Germer at Bell Telephone Laboratories. They fired a beam of electrons at a crystal of nickel and observed something that should have been impossible according to classical physics. The electrons created an interference pattern on the detector screen, displaying the characteristic wave behavior of constructive and destructive interference. Individual particles were somehow interfering with themselves, creating patterns that could only be explained if matter possessed an intrinsic wave nature. This discovery launched physics into uncharted territory where the familiar categories of waves and particles began to collapse into something far more mysterious. The same electrons that left distinct impact marks on photographic plates, like tiny bullets, also created spreading wave patterns that could bend around obstacles and interfere with themselves. The universe was revealing a fundamental duality that human language and classical concepts were inadequate to describe. The wave-particle duality extended beyond electrons to encompass every form of matter and energy. Neutrons displayed wave interference. Atoms created diffraction patterns. Even large molecules containing hundreds of atoms exhibited quantum wave behavior under carefully controlled conditions. The boundary between the quantum and classical worlds wasn't determined by some magical dividing line, but rather by the practical limitations of measurement and the overwhelming complexity of large-scale systems. So, this revelation forced scientists to confront an uncomfortable truth about the nature of scientific knowledge itself. The properties we observe in objects depend fundamentally on how we choose to observe them. Design an experiment to detect particle behavior, and particles are what you find. Design an experiment to detect wave behavior, and waves emerge from the same quantum system. The act of measurement doesn't simply reveal pre-existing properties, it participates in creating the reality we observe. The implications of this measurement problem became even more disturbing when physicists attempted to observe both wave and particle properties simultaneously. Werner Heisenberg discovered that certain pairs of properties, like position and momentum, could never be measured with perfect precision at the same time. The more accurately you determine where a particle is located, the less you can know about how fast it's moving. This wasn't a limitation of measurement technology or experimental technique. It represented a fundamental feature of quantum reality itself. Heisenberg's uncertainty principle, formulated in 1927, established mathematical limits on simultaneous knowledge of complementary properties. The product of uncertainties in position and momentum must always exceed Planck's constant divided by 4 pi. This relationship revealed that uncertainty wasn't an unfortunate consequence of imperfect measurements, but rather an inescapable characteristic of quantum systems. Nature itself maintains a veil of probabilistic indeterminacy that no amount of technological sophistication can penetrate. The uncertainty principle shattered the deterministic worldview that had dominated physics since Newton. Classical mechanics promised that perfect knowledge of initial conditions would allow perfect prediction of future states. Every event was the inevitable consequence of prior causes unfolding according to mathematical laws. But quantum mechanics revealed that nature itself is fundamentally probabilistic. Even with complete knowledge of a quantum system, you can only calculate the likelihood of various measurement outcomes, never predict with certainty what will happen in any individual case. This probabilistic nature of quantum mechanics troubled many physicists, including Einstein, who famously declared that God does not play dice with the universe. Einstein spent decades searching for hidden variable theories that might restore deterministic causality to physics. He proposed thought experiments designed to reveal the supposedly incomplete nature of quantum theory. Each time, careful analysis showed that quantum mechanics provided complete and consistent descriptions of natural phenomena, even when those descriptions violated classical intuitions about reality. The most famous of these thought experiments involved two particles that had interacted and then separated by vast distances. According to quantum mechanics, measuring a property of one particle would instantaneously influence the measurement outcomes for the other particle, regardless of the spatial separation between them. Einstein derided this as spooky action at a distance and argued that it proved quantum theory was incomplete. Surely, he reasoned, the particles must possess definite properties, independent of measurement, properties that predetermine the correlations we observe. Decades later, physicist John Bell developed mathematical tests that could distinguish between Einstein's hidden variable theories and the predictions of quantum mechanics. When these tests were performed in the 1970s and 1980s, the results consistently supported quantum mechanics and ruled out local hidden variable theories. The universe really does exhibit the strange non-local correlations that Einstein found so troubling. Particles separated by astronomical distances can influence each other's properties instantaneously, not through any physical signal or force, but through the mysterious quantum entanglement that links their fates. These experimental confirmations of quantum non-locality forced physicists to abandon comfortable assumptions about the independence and locality of physical systems. Reality isn't composed of separate objects interacting through local forces across space and time. Instead, quantum systems can form entangled wholes where the properties of individual parts have no independent existence. The measurement of one component instantaneously affects the entire system, revealing correlations that transcend classical notions of space and causality. The quantum revolution that began with Planck's desperate mathematical fix had evolved into something far more profound than anyone could have anticipated. Energy quantization was just the first glimpse into a deeper quantum reality where particles exist in superposition states, where measurement creates rather than reveals properties, and where entanglement connects distant systems through invisible quantum threads. Each new discovery revealed additional layers of strangeness that challenged fundamental assumptions about the nature of existence. Yet even these mind-bending revelations were just the 20th century would eventually lead to technologies that transform beginning. The quantum principles discovered in the early and magnetic resonance imaging all emerged from practical human civilization. Lasers, transistors, computer chips applications of quantum mechanics. The same strange physics that seemed to violate common sense became the foundation for the modern technological world. The quantum realm also opened doors to possibilities that bordered on science fiction. Quantum computers promised to solve certain problems exponentially faster than classical machines by exploiting superposition and entanglement. Quantum cryptography offered theoretically unbreakable security based on the fundamental laws of physics. Quantum teleportation demonstrated the ability to transfer quantum states across arbitrary distances, though not in the way popular culture might imagine. But perhaps the most profound impact of the quantum revolution was philosophical rather than technological. Quantum mechanics forced humanity to confront the limits of classical reasoning and objective reality. The universe revealed itself to be far stranger and more interconnected than our evolved intuitions suggested. Consciousness and measurement became inextricably linked to physical processes in ways that continue to generate debate among philosophers and physicists. As we stand at the threshold of a new quantum age, with quantum computers beginning to demonstrate practical advantages and quantum technologies reshaping entire industries, we can trace the origins of this transformation back to Max Planck's reluctant hypothesis. His desperate attempt to resolve the ultraviolet catastrophe accidentally opened a doorway to understanding the deepest structures of reality itself. The discrete energy packets he introduced to save a failing theory became the foundation for a complete reimagining of physics and our place within the cosmic order. The story of quantum mechanics doesn't end with philosophical puzzles and theoretical breakthroughs. The same bizarre principles that seemed to mock human intuition would eventually spawn technologies that transformed civilization itself. But the path from Planck's mathematical desperation to practical quantum applications required decades of additional discoveries, each more counterintuitive than the last. In 1926, Austrian physicist Erwin Schrödinger developed a mathematical framework that could predict the behavior of quantum systems with unprecedented precision. His wave equation described how quantum states evolve over time, treating particles as probability waves that spread through space according to mathematical rules. This equation became the foundation of quantum mechanics, providing scientists with tools to calculate the likelihood of finding particles in specific locations or states. Schrödinger's equation revealed something extraordinary about the quantum world. Particles didn't follow definite paths through space like classical objects. Instead, they existed as probability clouds that could occupy multiple positions simultaneously. An electron orbiting an atomic nucleus wasn't located at any specific point until someone measured its position. Before measurement, it existed in what physicists call a superposition state, simultaneously occupying all possible locations with different probabilities. This superposition principle extends far beyond simple position measurements. Quantum particles can exist in combinations of different energy states, different spin orientations, or different momentum values simultaneously. They remain in these ghostly superposition states until interaction with a measurement device forces them to collapse into definite classical properties. The mathematics of quantum mechanics could predict the probabilities of various outcomes, but individual measurements remained fundamentally unpredictable. The implications of superposition challenged every assumption about the nature of existence. Classical physics assumed that objects possess definite properties independent of observation. A baseball has a specific position and velocity, whether anyone measures them or not, but quantum mechanics suggested that microscopic systems don't possess definite properties until measurement creates them. The act of observation doesn't simply reveal pre-existing reality, it participates in constructing the reality we observe. Schrödinger himself found these implications so disturbing that he devised a thought experiment to highlight their apparent absurdity. Imagine a cat sealed inside a box with a quantum system that has a 50% chance of decaying within an hour. If the system decays, it triggers a mechanism that kills the cat. According to quantum mechanics, before anyone opens the box, the quantum system exists in a superposition of decayed and non-decayed states. This means the cat should somehow be both alive and dead simultaneously until observation collapses the superposition into a definite outcome. The paradox of Schrödinger's cat exposed the measurement problem that continues to perplex physicists today. How does the fuzzy quantum world of superpositions and probabilities give rise to the definite classical world we experience? When exactly does quantum superposition collapse into classical reality? These questions probe the boundary between microscopic quantum mechanics and macroscopic classical physics, revealing deep mysteries about the nature of measurement and consciousness. While philosophers debated the meaning of quantum mechanics, experimental physicists continued uncovering new phenomena that pushed the boundaries of strangeness even further. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a paper describing what they considered the most troubling aspect of quantum theory. They showed that quantum mechanics predicted correlations between distant particles that seemed to violate the principle that no influence can travel faster than light. Consider two particles created in a quantum interaction and then separated by vast distances. According to quantum mechanics, measuring a property of one particle instantly determines the corresponding property of the other particle, regardless of the space between them. If you measure the spin of particle A and find it pointing upward, you immediately know that particle B's spin points downward, even if B is located on the other side of the galaxy. This instantaneous correlation troubled Einstein because it seemed to require faster-than-light communication between the particles. Einstein argued that this spooky action at a distance proved quantum mechanics was incomplete. He proposed that particles must possess hidden properties that predetermined their measurement outcomes, eliminating the need for mysterious instantaneous influences. Local hidden variable theories could explain quantum correlations without violating the speed of light limit, preserving the classical notion that objects have definite properties independent of measurement. The debate between Einstein and the quantum establishment remained largely philosophical until 1964, when physicist John Bell derived mathematical inequalities that could distinguish between hidden variable theories and quantum mechanics. Bell's theorem showed that any theory based on local hidden variables must satisfy certain statistical constraints. If experiments violated these Bell inequalities, it would prove that nature really does exhibit the non-local correlations predicted by quantum mechanics. The first decisive tests of Bell's inequalities were performed in the 1970s by physicists like John Clauser and Stuart Friedman. Their experiments used pairs of entangled photons to measure correlations that violated Bell's inequalities by substantial margins. Subsequent experiments closed various potential loopholes and confirmed that quantum mechanics correctly describes nature's non-local behavior. Einstein's hidden variables simply don't exist, at least not in any form that preserves locality and realism. These experimental confirmations of quantum non-locality revealed that reality is far more interconnected than classical physics suggested. Entangled particles form unified quantum systems where individual components lack independent existence. Measuring one part of an entangled system instantly affects the entire system, creating correlations that transcend space and time. The universe isn't composed of separate objects interacting through local forces. Instead, quantum entanglement weaves everything into an invisible web of instantaneous connections. The practical implications of entanglement began to emerge in the 1990s as physicists developed quantum information theory. They realized that quantum superposition and entanglement could be harnessed to perform computational tasks impossible with classical systems. A quantum computer could exist in superpositions of different computational states simultaneously, potentially solving certain problems exponentially faster than any classical machine. The key insight was that quantum bits, or qubits, could store vastly more information than classical bits. While a classical bit must be either 0 or 1, a qubit can exist in superposition states that are simultaneously 0 and 1 until measurement forces it to collapse. Multiple qubits can be entangled to create computational states that represent enormous numbers of possibilities simultaneously. Quantum algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases demonstrated the potential power of quantum computation. These algorithms could break current encryption schemes and accelerate database searches using principles that seem to violate common sense. The quantum computer would explore multiple solution paths simultaneously through superposition, using quantum interference to amplify correct answers and cancel incorrect ones. Building practical quantum computers proved extraordinarily challenging because quantum superposition states are incredibly fragile. Any interaction with the environment can cause decoherence, destroying the quantum properties that make quantum computation powerful. Physicists had to develop sophisticated error correction techniques and isolation methods to maintain quantum coherence long enough for useful calculations. Despite these challenges, the first primitive quantum computers began demonstrating quantum advantages in specific tasks by the 2010s. Companies like IBM, Google, and IonQ built quantum processors with dozens of qubits, achieving quantum supremacy in carefully designed problems. While these early machines couldn't yet outperform classical computers in practical applications, they proved that quantum computation was technologically feasible. The development of quantum technologies extended far beyond computation. Quantum cryptography exploited the fundamental properties of quantum mechanics to create theoretically unbreakable communication channels. Any attempt to eavesdrop on quantum encrypted messages would disturb the quantum states being transmitted, alerting the legitimate users to the security breach. This quantum key distribution provided security guaranteed by the laws of physics rather than mathematical complexity. Quantum sensors leveraged the sensitivity of quantum systems to measure physical quantities with unprecedented precision. Atomic clocks based on quantum transitions achieved accuracies that could detect the gravitational time dilation caused by elevation changes of just centimeters. Quantum magnetometers could detect magnetic fields millions of times weaker than those sensed by classical instruments. These ultra-sensitive quantum sensors opened new possibilities for fundamental physics research and practical applications from medical imaging to navigation systems. The strangest quantum technology of all was quantum teleportation, which could transfer quantum states from one location to another without physically moving the particles involved. This process relied on quantum entanglement to create correlations between distant particles, allowing the quantum state of one particle to be reconstructed at a remote location. While quantum teleportation couldn't transport macroscopic objects like science fiction suggested, it enabled secure quantum communication networks spanning continental distances. As quantum technologies matured from laboratory curiosities into practical devices, they began revealing new aspects of quantum mechanics that even its founders hadn't anticipated. Researchers discovered quantum effects in biological systems, suggesting that evolution had learned to exploit quantum mechanics millions of years before humans understood it existed. Photosynthesis appears to use quantum coherence to achieve near-perfect energy transfer efficiency. Bird navigation might rely on quantum entanglement in specialized proteins that can detect Earth's magnetic field. These discoveries in quantum biology challenged assumptions about where quantum effects could survive. Living systems are warm, wet, and noisy environments that should destroy quantum coherence almost instantly. Yet natural selection seems to have found ways to protect and exploit quantum properties for biological advantage. This suggests that the boundary between quantum and classical physics is more subtle and context-dependent than previously thought. The quantum revolution also transformed our understanding of space and time themselves. Quantum field theory, which merged quantum mechanics with Einstein's special relativity, revealed that empty space isn't truly empty but filled with quantum fluctuations that constantly create and destroy virtual particle pairs. These vacuum fluctuations have measurable effects, producing phenomena like the Casimir force between closely spaced conducting plates. Even more remarkably, quantum mechanics suggested that space and time might emerge from more fundamental quantum information structures. Some physicists propose that reality consists of networks of quantum entanglement that give rise to space-time geometry through emergent processes we don't yet fully understand. If these theories prove correct, Planck's energy quanta might be just the tip of an iceberg, hiding deeper quantum foundations of existence itself. The journey from Planck's reluctant hypothesis to modern quantum technologies demonstrates how scientific revolutions unfold in unexpected ways. What began as a mathematical trick to fix a broken equation evolved into a complete reimagining of reality's fundamental nature. Each new discovery revealed additional layers of quantum strangeness that pushed the boundaries of human comprehension further into uncharted territory. Today's quantum scientists work with phenomena that would have seemed like magic to researchers just decades ago. They manipulate individual atoms with laser light, create entanglement between particles separated by intercontinental distances, and build computers that perform calculations by existing in multiple states simultaneously. Yet these remarkable achievements represent just the beginning of humanity's exploration into the quantum realm. The principles that Planck discovered in his desperate attempt to understand blackbody radiation continue driving scientific progress more than a century later. Quantum mechanics has become the most precisely tested theory in the history of science, making predictions confirmed to extraordinary accuracy across countless experiments. Its mathematical formalism provides the foundation for understanding everything from the behavior of electrons in computer chips to the fusion reactions powering stars. But perhaps the most profound legacy of Planck's quantum hypothesis lies not in its technological applications or mathematical precision, but in how it transformed humanity's relationship with the natural world. The quantum revolution revealed that reality operates according to principles that transcend human intuition and classical reasoning. It forced us to abandon comfortable assumptions about determinism, locality, and the independent existence of physical properties. As we stand on the threshold of a quantum future where quantum computers may solve previously intractable problems and quantum technologies enable capabilities beyond current imagination, we carry with us the humbling lesson that nature's deepest secrets often hide behind the most mundane phenomena. Planck's investigation of how hot objects glow opened doorways to understanding the most fundamental aspects of existence. Who knows what revolutionary discoveries await in the seemingly ordinary problems that today's scientists struggle to solve? The quantum fabric of reality continues revealing new patterns and possibilities with each passing year. From the cosmic scale of black holes and dark matter to the subatomic realm of quarks and neutrinos, quantum mechanics provides the conceptual framework for understanding how the universe operates at its most basic level. The same principles that emerged from studying thermal radiation now guide our exploration of parallel universes, time travel, and the ultimate fate of cosmic evolution itself. The quantum realm that Planck accidentally discovered was only beginning to reveal its most disturbing secrets. As physicists delved deeper into the mathematical foundations of his energy packets, they uncovered layers of reality so bizarre that human language itself proved inadequate to describe them. The comfortable world of solid objects and predictable outcomes was dissolving into something far more mysterious and unsettling. In the 1940s, American physicist Richard Feynman developed a revolutionary approach to understanding quantum mechanics that would make the strangeness even more apparent. Instead of thinking about particles following single paths through space, Feynman proposed that quantum particles simultaneously explore every possible path between 2 points. A photon traveling from a light source to a detector doesn't take just one route through space. It takes all possible routes simultaneously, including paths that loop backward through time, spiral around distant galaxies, and venture to the edge of the observable universe before returning. This many paths interpretation of quantum mechanics sounds like science fiction, but its mathematical predictions match experimental results with extraordinary precision. When you add up the contributions from all possible paths, most cancel each other out through quantum interference, leaving only the paths that correspond to classical physics. The familiar world we experience emerges from the quantum chaos like a calm surface hiding turbulent currents beneath. Feynman's path integral formulation revealed something deeply unsettling about the nature of quantum reality. Every quantum process involves the particle simultaneously experiencing every conceivable way the process could unfold. An electron doesn't simply jump from one atomic orbit to another. It explores every possible trajectory between those orbits, including routes that violate energy conservation and take arbitrary amounts of time. Only when the quantum calculation is complete do the impossible paths cancel out, leaving behavior that appears to follow physical laws. This quantum exploration of multiple realities simultaneously became even more disturbing when physicists realized it applied to the entire universe. If individual particles could exist in superposition states exploring multiple possibilities, then entire systems of particles could exist in superpositions of different configurations. The universe itself might exist in a quantum superposition of all possible histories, with our classical experience representing just one strand in an infinite tapestry of parallel realities. The mathematical framework for describing these quantum superpositions grew increasingly sophisticated throughout the 20th century. Physicists developed techniques for calculating how quantum systems evolve through complex mathematical spaces called Hilbert spaces, where each point represents a possible configuration of the system. These calculations revealed that quantum mechanics wasn't just a theory about tiny particles, it was a fundamental description of how information and reality itself operate at the deepest level. The information theoretic aspects of quantum mechanics became particularly important as physicists began to understand that quantum systems could store and process information in ways impossible for classical systems. A quantum bit could exist in superposition states that simultaneously represented multiple pieces of information. Multiple quantum bits could be entangled to create collective states that encoded exponentially more information than the individual bits could store separately. This quantum information processing capability suggested that the universe itself might operate as a vast quantum computer, with every particle and field contributing to an ongoing computation that determines how reality evolves. The physical laws we observe might emerge from underlying quantum computational processes, making the universe simultaneously the computer and the program it runs. The implications of this quantum computational view of reality extended far beyond physics into philosophy and cosmology. If the universe operates as a quantum computer, then questions about the nature of consciousness, free will, and the meaning of existence take on entirely new dimensions. Consciousness itself might represent a particular type of quantum information processing that emerges when sufficiently complex quantum systems develop the ability to model themselves. Some physicists propose that consciousness plays a fundamental role in quantum mechanics by causing the collapse of superposition states into definite classical outcomes. This interpretation suggested that observation by conscious beings literally creates the reality we experience from the quantum possibilities that exist before measurement. The universe would remain in a ghostly superposition of all possible states until conscious observers force it to choose definite outcomes through their measurements. This consciousness-based interpretation of quantum mechanics attracted fierce debate among physicists and philosophers. Critics argued that it gave consciousness an unwarranted privileged role in physics and failed to explain how consciousness itself could arise from quantum processes. Supporters countered that consciousness represented the only known phenomenon capable of converting quantum possibilities into classical realities, making it an essential component of any complete theory of nature. Alternative interpretations of quantum mechanics avoided invoking consciousness, but introduced their own unsettling implications. The many worlds interpretation proposed that every quantum measurement creates a branching of reality into parallel universes, each containing different outcomes. In this view, every possible result of every quantum process actually occurs, but in separate branches of an ever-expanding multiverse. You experience only one branch of this cosmic tree, while countless other versions of yourself experience different outcomes in parallel realities. The many worlds interpretation eliminated the measurement problem by denying that quantum superpositions ever truly collapse. Instead, they argued that superposition states simply become correlated with the environment in ways that create the appearance of collapse from the perspective of observers within each branch. Every quantum possibility remains equally real, existing in its own parallel universe where different versions of history unfold according to alternative quantum outcomes. This proliferation of parallel universes raises profound questions about personal identity and the nature of existence. If countless versions of yourself exist across the multiverse, experiencing every possible variation of your life story, then what makes your particular branch of reality special? The version of you reading these words represents just one strand in an infinite web of parallel selves, each convinced that their reality is the only true one. The mathematical machinery of quantum mechanics remained indifferent to these philosophical puzzles, continuing to make precise predictions about experimental outcomes regardless of how physicists interpreted its meaning. Quantum field theory extended the quantum framework to describe the creation and annihilation of particles themselves, revealing that the vacuum of empty space seethes with quantum fluctuations that constantly create and destroy virtual particle pairs. These vacuum fluctuations have measurable effects on physical systems. They shift the energy levels of atoms in ways that can be detected with extraordinary precision. They create forces between conducting plates separated by tiny gaps. They contribute to the cosmological constant that drives the accelerating expansion of the universe. The apparent emptiness of space turns out to be filled with quantum activity that influences every physical process. Quantum field theory also revealed that particles themselves are better understood as excitations in underlying quantum fields that permeate all of space and time. An electron isn't a tiny sphere of matter, but rather a localized disturbance in the electron field. A photon represents an excitation in the electromagnetic field. This field-based picture of matter and energy dissolved the classical distinction between particles and waves into something more fundamental and abstract. The quantum fields that underlie all matter and energy interact with each other in ways governed by symmetry principles that determine the basic forces of nature. The electromagnetic force emerges from the symmetries of the electromagnetic field. The weak nuclear force that governs radioactive decay arises from different field symmetries. The strong nuclear force that binds protons and neutrons in atomic nuclei comes from yet another set of field symmetries. This unification of forces through quantum field theory represented one of the greatest triumphs of the 20th century physics. The Standard Model of particle physics successfully described three of the four fundamental forces using a single quantum field theory framework. Only gravity remained outside this unified description, requiring Einstein's general relativity to describe its effects on space and time. The search for a quantum theory of gravity has dominated theoretical physics for decades, with approaches ranging from string theory to loop quantum gravity to emergent spacetime theories. Each approach suggests that space and time themselves might be emergent phenomena arising from more fundamental quantum structures. If these theories prove correct, then Planck's energy quanta represent just the visible tip of a vast quantum iceberg that includes the very fabric of space-time itself. String theory proposes that the fundamental constituents of reality are tiny vibrating strings rather than point particles. Different vibration patterns of these strings correspond to different particles and forces, potentially unifying all of physics into a single framework. The theory requires additional spatial dimensions beyond the three we experience, with these extra dimensions curled up so small that we cannot detect them directly. Loop quantum gravity takes a different approach, suggesting that space itself is quantized at the smallest scales. Instead of being infinitely divisible, space consists of discrete quantum units linked together in networks that give rise to smooth geometry at larger scales. This quantization of space would eliminate the mathematical infinities that plague attempts to combine quantum mechanics with general relativity. Emergent spacetime theories propose that space and time arise from quantum entanglement networks, where the geometry of spacetime reflects the patterns of quantum correlations between different regions. In this view, the familiar three-dimensional space we inhabit emerges from underlying quantum information structures that operate according to principles we are only beginning to understand. These cutting-edge theories push the boundaries of quantum mechanics far beyond Planck's original energy quantization. They suggest that reality consists of quantum information processing at the most fundamental level, with all the familiar features of the physical world emerging from deeper quantum computational processes. Matter, energy, space, and time become different aspects of an underlying quantum reality that operates according to information theoretic principles. The technological implications of these advanced quantum theories remain largely speculative, but they hint at possibilities that border on the fantastical. Quantum computers that exploit higher dimensional spaces might solve problems that are impossible even for idealized classical computers. Quantum communication networks might enable secure information transfer across cosmological distances. Quantum sensors might detect gravitational waves from the Big Bang itself or probe the quantum structure of spacetime directly. Even more speculative possibilities emerge from theories that treat consciousness as a fundamental feature of quantum reality. If consciousness represents a particular type of quantum information processing, then sufficiently advanced quantum technologies might enable direct interfacing between human minds and quantum systems. This could lead to forms of enhanced cognition that exploit quantum superposition and entanglement to process information in ways that transcend current human limitations. The journey from Planck's desperate mathematical fix to these speculative frontiers of quantum reality demonstrates how scientific revolutions unfold through unexpected pathways. What began as an attempt to understand thermal radiation has evolved into a complete reconceptualization of the nature of existence itself. Each new discovery in quantum mechanics has revealed additional layers of strangeness that challenge our most basic assumptions about reality. As quantum technologies mature from laboratory experiments into practical applications, they continue to reveal new aspects of the quantum world that even its pioneering discoverers never anticipated. Quantum computers are beginning to demonstrate computational advantages that classical systems cannot match. Quantum communication networks are enabling secure information transfer over intercontinental distances. Quantum sensors are achieving measurement precisions that approach fundamental quantum limits. Yet these remarkable technological achievements represent just the beginning of humanity's exploration into the quantum realm. The principles that Planck reluctantly introduced to save classical physics have grown into a comprehensive framework for understanding reality at its most fundamental level. Every new experiment probes deeper into the quantum foundations of existence, revealing phenomena that continue to surprise and perplex even expert physicists. The quantum mechanical description of nature has become the most precisely tested theory in the history of science, with predictions confirmed to accuracies that exceed 1 part in a trillion. Yet the meaning of these precise mathematical relationships remains as mysterious today as it was when Planck first proposed energy quantization. The quantum world operates according to principles that transcend human intuition, forcing us to accept mathematical descriptions of phenomena that we cannot visualize or comprehend through classical reasoning. This tension between mathematical precision and conceptual mystery reflects a deeper truth about the nature of scientific understanding. The most fundamental aspects of reality often hide behind the most ordinary phenomena, waiting to be discovered by investigators willing to follow mathematical logic wherever it leads. Planck's investigation of thermal radiation opened doorways to understanding the deepest structures of existence, demonstrating that revolutionary insights can emerge from the most mundane scientific problems. The quantum revolution continues to unfold in directions that its founders could never have imagined. From quantum biology to quantum cosmology, from quantum computation to quantum consciousness, the principles discovered through studying blackbody radiation have become the foundation for exploring every aspect of natural phenomena. The same mathematical framework that emerged from Planck's desperate attempt to fix classical physics now guides our understanding of everything from the behavior of molecules in living cells to the evolution of the entire universe. As we stand at the threshold of a quantum technological revolution that promises to transform human civilization as profoundly as the Industrial Revolution did centuries ago, we carry with us the humbling recognition that nature's deepest secrets often reveal themselves through the most unexpected pathways. The quantum fabric of reality continues to surprise us with each new discovery, reminding us that the universe operates according to principles far stranger and more wonderful than our everyday experience suggests. The quantum realm that Planck's equations had accidentally unlocked was preparing to reveal secrets so profound that they would force humanity to question the very nature of existence itself. As the 20th century progressed, physicists began to realize that the strange behaviors they observed in laboratory experiments might reflect something far more fundamental than anyone had dared to imagine. The universe wasn't simply governed by quantum mechanics. The universe might actually be quantum mechanics, operating as a vast information processing system where reality emerges from computational processes too complex for human minds to fully grasp. This realization began to crystallize in the 1960s when physicists started examining the mathematical structure of quantum mechanics from an entirely new perspective. Instead of focusing on particles and waves, they began studying the flow of information through quantum systems. What they discovered was deeply unsettling. Information in the quantum world doesn't behave like information in our everyday experience. It can exist in superposition states where multiple pieces of information occupy the same quantum system simultaneously. It can be entangled across vast distances, creating instantaneous correlations that transcend space and time. Most disturbing of all, quantum information can be processed in ways that allow computations to explore multiple solution paths simultaneously. The implications of this quantum information perspective began to reshape our understanding of everything from the smallest subatomic particles to the largest structures in the cosmos. If information represents the fundamental currency of reality, then the classical world we experience might be nothing more than a simplified approximation of underlying quantum computational processes. Every atom, every molecule, every biological cell might be participating in vast information processing networks that give rise to the phenomena we observe through our limited classical senses. This information theoretic view of quantum mechanics gained tremendous support from advances in computer science and mathematics. Researchers discovered that certain computational problems that would require classical computers longer than the age of the universe to solve could potentially be solved by quantum computers in mere minutes or hours. The key lay in quantum superposition, which allows quantum bits to exist in combinations of 0 and 1 simultaneously, enabling quantum computers to explore multiple computational paths in parallel. But the true power of quantum computation emerged when physicists learned to harness quantum entanglement for information processing. Entangled quantum bits could be manipulated as unified systems, creating collective computational states that encode exponentially more information than classical systems could handle. A quantum computer with just 300 quantum bits could simultaneously process more computational states than there are atoms in the observable universe. This exponential scaling suggested that quantum systems possess computational capabilities that dwarf anything achievable through classical means. The development of practical quantum computers required overcoming extraordinary technical challenges that pushed the boundaries of human engineering capability. Quantum superposition states are incredibly fragile, destroyed by the slightest interaction with the surrounding environment. Physicists had to develop sophisticated techniques for isolating quantum systems from external disturbances while still maintaining enough control to perform useful computations. They created quantum error correction protocols that could detect and fix errors without destroying the delicate quantum states they were trying to protect. These technological achievements began to blur the line between theoretical physics and practical engineering in unprecedented ways. Quantum computers required operating temperatures colder than interstellar space, magnetic field controls more precise than those used in the most sensitive scientific instruments, and timing accuracies measured in fractions of nanoseconds. Building these machines demanded a level of technological sophistication that pushed multiple branches of engineering to their absolute limits. As the first primitive quantum computers came online in the early 21st century, they began to demonstrate computational behaviors that seemed to violate the normal rules of information processing. These machines could solve certain types of mathematical problems by appearing to consult multiple parallel universes simultaneously, exploring solution spaces that contained more possibilities than classical physics should allow. The quantum algorithms running on these computers seem to tap into computational resources that existed beyond the confines of our single classical reality. The philosophical implications of these quantum computational capabilities proved even more disturbing than their technological potential. If quantum computers could access information processing resources beyond classical physics, what did this suggest about the nature of reality itself? Some physicists began to propose that our universe operates as a quantum computer, with every particle and field contributing to an ongoing cosmic computation that determines how physical laws unfold over time. This computational view of the universe suggested that the familiar world of objects and events might represent the output of underlying quantum computational processes. The laws of physics wouldn't be fundamental principles governing reality, but rather emergent patterns arising from deeper informational structures. Space, time, matter, and energy could all be different aspects of quantum information processing occurring at scales and speeds beyond human comprehension. The evidence supporting this radical reinterpretation of reality began accumulating from multiple directions. Quantum field theory revealed that the vacuum of empty space contains virtually unlimited amounts of quantum information encoded in fluctuating fields that constantly create and destroy virtual particles. These vacuum fluctuations carry out computations that determine how real particles behave when they interact. The apparent emptiness of space turns out to be filled with information processing activity that influences every physical process in the universe. Black holes presented another compelling example of information processing in extreme physical environments. Theoretical calculations suggested that black holes contain enormous amounts of information encoded on their event horizons, with each bit of information corresponding to a fundamental unit of area. As matter falls into a black hole, the information it carries becomes encoded in the quantum structure of the event horizon, where it participates in computational processes that determine how the black hole evolves over cosmic timescales. The holographic principle that emerged from black hole physics suggested that all the information contained in any volume of space could be encoded on the boundary surface of that volume. This principle implied that our three-dimensional reality might be a projection of information processing occurring on a two-dimensional surface, similar to how a hologram creates three-dimensional images from information stored in two dimensions. If the holographic principle applies to the entire universe, then everything we experience as solid three-dimensional reality might be the output of computational processes occurring on a distant cosmic boundary. These discoveries in theoretical physics began to converge with developments in quantum biology that revealed information processing capabilities in living systems. Photosynthesis, the fundamental process that powers most life on Earth, appears to use quantum coherence to achieve energy transfer efficiencies that approach theoretical limits. Plants and bacteria exploit quantum superposition to explore multiple energy transfer pathways simultaneously, selecting the most efficient routes through quantum mechanical optimization processes. Bird navigation systems also seem to rely on quantum effects, using specialized proteins that can maintain quantum coherence in the warm, noisy environment of living cells. These biological quantum sensors can detect the Earth's magnetic field by exploiting quantum entanglement between electron pairs, providing navigation information with extraordinary precision. The discovery that evolution had learned to harness quantum mechanics millions of years before humans understood its existence suggested that quantum information processing might be fundamental to life itself. Even more remarkably, some researchers began investigating whether consciousness itself might represent a particular type of quantum information processing. The human brain contains approximately 100 billion neurons, each connected to thousands of others through synaptic networks that process information in ways that remain poorly understood. If consciousness emerges from quantum computational processes occurring in neural microtubules or other cellular structures, then human awareness might represent our direct experience of quantum information processing in action. This quantum theory of consciousness suggested that the subjective experience of being aware might correspond to the collapse of quantum superposition states in neural networks. The stream of consciousness could represent the ongoing selection of definite outcomes from quantum possibilities, with each conscious moment corresponding to the resolution of quantum computational processes in the brain. Free will might emerge from quantum indeterminacy in neural networks, allowing conscious beings to influence their own behavior through quantum choices that transcend classical determinism. These speculative connections between quantum mechanics and consciousness remained highly controversial among scientists and philosophers. Critics argued that the brain operates as a classical system where quantum effects would be destroyed by thermal noise and environmental decoherence. They pointed out that no clear mechanism existed for quantum coherence to persist in the warm, wet environment of neural tissue. Supporters countered that biological systems had demonstrated remarkable abilities to maintain quantum coherence under seemingly impossible conditions, suggesting that consciousness might exploit similar protective mechanisms. Regardless of the ultimate resolution of the consciousness debate, the broader trend toward understanding reality as quantum information processing continued to gain momentum. Advances in quantum field theory revealed that fundamental particles themselves might be better understood as patterns of information flow rather than discrete objects with inherent properties. The standard model of particle physics, despite its tremendous experimental success, began to appear as an approximation of deeper informational structures that determine how quantum fields interact. String theory and other approaches to quantum gravity suggested that even space and time might emerge from quantum information processing at the smallest scales. In these theories, the familiar three-dimensional space we inhabit represents a low-energy approximation of higher-dimensional informational structures. The geometry of space-time reflects the patterns of quantum entanglement between different regions, with gravity emerging as a consequence of information flow through quantum networks that exist beyond ordinary space and time. These developments in theoretical physics suggested that Planck's original insight about energy quantization represented just the first glimpse of a far more comprehensive quantum description of reality. The discrete energy packets that he reluctantly introduced to explain blackbody radiation had evolved into a complete framework for understanding existence as quantum information processing. Every phenomenon, from the behavior of subatomic particles to the evolution of galaxies, could potentially be understood as the output of computational processes occurring in quantum networks that span the observable universe. The technological implications of this information theoretic view of reality promised to revolutionize human civilization in ways that made previous technological revolutions appear modest by comparison. Quantum computers that could exploit the computational resources of parallel universes might solve problems that are impossible for any classical system. Quantum communication networks might enable instantaneous information transfer across cosmic distances through entanglement-based protocols that transcend the speed of light limitation. Even more speculative possibilities emerged from theories that treated consciousness as quantum information processing. If human awareness really does emerge from quantum computational processes, then advanced quantum technologies might enable direct interfacing between minds and quantum computers. This could lead to forms of enhanced cognition that transcend the limitations of biological neural networks, allowing human consciousness to process information using quantum superposition and entanglement. The potential for quantum enhancement of human cognitive capabilities raised profound ethical and philosophical questions about the future of human nature itself. If consciousness could be augmented through quantum technologies, what would distinguish enhanced humans from artificial intelligences that operated according to similar quantum computational principles? The boundaries between human and machine intelligence might dissolve as both forms of cognition began to exploit the same underlying quantum information processing capabilities. These far-reaching implications of the quantum revolution demonstrated how Planck's mathematical desperation had accidentally opened doorways to understanding the deepest possible questions about existence, consciousness, and the nature of reality. What began as an attempt to fix a broken equation about thermal radiation had evolved into a comprehensive framework for reconceptualizing everything from the smallest particles to the largest cosmic structures as manifestations of quantum information processing. The journey from Planck's energy packets to quantum theories of consciousness and reality illustrated how scientific revolutions unfold through pathways that their initiators could never have anticipated. Each new discovery revealed additional layers of quantum strangeness that pushed the boundaries of human understanding further into territories that transcended classical reasoning. The mathematical precision of quantum mechanics provided tools for making accurate predictions about natural phenomena, but the meaning of these mathematical relationships remained as mysterious and counterintuitive as ever. as quantum technologies began to mature from laboratory curiosities into practical applications that could transform entire industries. They continued to reveal new aspects of quantum mechanics that surprised even expert physicists. Quantum computers demonstrated computational capabilities that seemed to violate classical limits on information processing. Quantum communication networks achieved security guarantees that depended on fundamental properties of quantum mechanics rather than mathematical complexity. Quantum sensors reached precision levels that approached theoretical limits imposed by quantum uncertainty itself. Yet these remarkable technological achievements represented just the beginning of humanity's exploration into the quantum foundations of existence. The principles that emerged from studying black-body radiation continued to drive scientific progress in directions that pushed the boundaries of human knowledge toward questions that had traditionally belonged to philosophy and theology. The quantum mechanical description of nature had become a gateway to understanding the most fundamental aspects of reality, consciousness, and the meaning of existence itself. The mathematical framework of quantum mechanics provided unprecedented precision in predicting experimental outcomes, but it also forced physicists to abandon comfortable assumptions about determinism, locality, and the independent existence of physical properties. The quantum world operated according to principles that transcended human intuition, revealing a universe far stranger and more interconnected than classical physics had suggested. Every new quantum discovery demonstrated that reality was more mysterious and wonderful than our everyday experience could possibly convey. As the 21st century progressed, the quantum revolution showed no signs of slowing down. Each new experimental breakthrough revealed additional phenomena that challenged existing theories and opened new directions for research. Quantum technologies began to impact fields ranging from medicine and materials science to cryptography and artificial intelligence. The same principles that Planck had reluctantly introduced to explain thermal radiation were becoming the foundation for understanding and manipulating matter, energy, and information at the most fundamental level. The story of quantum mechanics served as a powerful reminder that the most profound scientific discoveries often emerge from attempts to solve apparently mundane problems. Planck's investigation of how hot objects glow had uncovered principles that would eventually revolutionize human understanding of reality itself. This pattern suggested that revolutionary insights might be hiding behind other seemingly ordinary phenomena that current science struggles to explain. The quantum fabric of reality continued to surprise researchers with each new discovery, revealing layers of complexity and beauty that exceeded the wildest imagination. Looking toward the future, the quantum revolution promised to continue transforming human civilization in ways that would have seemed like magic to previous generations. Quantum computers might solve problems that could help design new materials, discover new medicines, and understand complex systems ranging from climate dynamics to economic markets. Quantum communication networks might enable forms of global coordination and cooperation that transcend current limitations imposed by distance and time delays. Perhaps most significantly, the quantum mechanical worldview was teaching humanity to embrace mystery and uncertainty as fundamental features of existence rather than problems to be solved. The quantum universe revealed itself as a realm where definitive answers gave way to probability distributions, where objective reality dissolved into observer-dependent descriptions, and where the act of measurement participated in creating the phenomena being observed. This shift from certainty to probability, from objectivity to participatory observation, represented a fundamental transformation in how humans related to the natural world. The quantum principles that emerged from Planck's desperate attempt to understand thermal radiation had grown into a comprehensive framework for exploring the deepest questions about the nature of existence. They provided tools for probing the boundaries between physics and consciousness, between determinism and free will, between individual identity and universal connection. The quantum revolution had become far more than a scientific theory. It had evolved into a new way of understanding humanity's place in a universe far more strange, interconnected, and wonderful than classical physics could ever have revealed. The quantum realm that Planck had accidentally unlocked was about to reveal its most disturbing secret of all. As physicists in the early decades of the 20th century struggled to understand the implications of energy quantization, they began to uncover evidence that the universe itself might not be the solid, predictable reality that human senses suggested. Instead, they were discovering that existence operates more like a vast probabilistic dance, where multiple realities compete for actualization until the moment of observation forces nature to choose. This realization emerged gradually through a series of experiments that grew increasingly difficult to explain using classical reasoning. When researchers fired individual electrons through carefully designed apparatus, they discovered behavior that should have been impossible according to everything science understood about matter. Single particles somehow knew about experimental setups they had never encountered, responding to changes made after they had already passed through the apparatus. The electrons seemed to possess a form of knowledge that transcended space and time, reacting to future measurements that hadn't yet occurred. The mathematical description of these phenomena required physicists to abandon the comfortable notion that particles possess definite properties independent of measurement. Instead, quantum mechanics suggested that particles exist in ghostly superposition states that encompass all possible properties simultaneously. An electron doesn't have a specific location or velocity until someone measures these quantities. Before measurement, it occupies a probabilistic cloud of potential outcomes that collapses into definite values only when interaction with a detector forces reality to make a choice. This collapse of quantum possibilities into classical outcomes represented one of the most mysterious aspects of the quantum world. The mathematics could predict the probabilities of various measurement results with extraordinary precision, but it provided no mechanism for understanding how or when the collapse occurred. The transition from quantum possibilities to classical realities remained hidden behind a veil of mathematical formalism that described what happened without explaining why it happened. Different schools of thought emerged to interpret this measurement problem, each offering radically different visions of reality's fundamental nature. Some physicists argued that consciousness played an essential role in causing quantum collapse, suggesting that the act of observation by aware beings literally created the classical world from quantum possibilities. Others proposed that every quantum measurement created parallel universes where each possible outcome occurred in separate branches of reality, meaning that every quantum event spawned countless parallel versions of the entire cosmos. The most conservative interpretation suggested that quantum mechanics simply represented the limits of human knowledge, rather than a fundamental feature of reality. According to this view, particles possessed definite properties that remained hidden from direct observation, with quantum probabilities reflecting our ignorance rather than genuine indeterminacy in nature. This hidden variable approach attempted to preserve classical notions of objective reality by pushing the mystery deeper into unobservable realms. Experimental tests designed to distinguish between these competing interpretations consistently supported the most radical implications of quantum mechanics. When physicists created pairs of particles that shared quantum entanglement and then separated them by vast distances, measurements on one particle instantly influenced the properties of its distant partner regardless of the space between them. These non-local correlations violated classical notions of locality and causality, demonstrating that the universe exhibits connections that transcend ordinary space and time. The confirmation of quantum non-locality forced scientists to accept that reality operates according to principles that fundamentally challenge human intuitions about independence and separation. Entangled systems behave as unified wholes where individual components lack independent existence, creating instantaneous correlations across arbitrary distances without any signal or influence traveling between the separated parts. The universe revealed itself to be far more interconnected than classical physics had suggested, with invisible quantum threads weaving everything into patterns of connection that operate beyond ordinary causation. These discoveries about quantum entanglement opened entirely new possibilities for understanding and manipulating information in ways that classical systems could never achieve. Entangled particles could be used to create communication channels that were fundamentally secure, since any attempt to intercept quantum information would disturb the entangled states and alert the legitimate users to the security breach. The laws of physics themselves guaranteed the privacy of quantum communication in ways that no classical encryption scheme could match. Even more remarkably, entanglement enabled a phenomenon that seemed to belong in science fiction rather than physics laboratories. Quantum teleportation allowed the complete transfer of quantum states from one location to another without physically moving the particles involved. This process exploited entanglement to reconstruct quantum information at distant locations, achieving perfect replication of quantum states across arbitrary distances. While quantum teleportation couldn't transport macroscopic objects like fictional transporters, it demonstrated that quantum information could transcend spatial limitations in ways that classical information never could. The development of quantum teleportation protocols required physicists to think about information itself in entirely new ways. Classical information could always be copied perfectly without disturbing the original, allowing unlimited reproduction of messages, images, or data. But quantum information obeyed a fundamental no-cloning theorem that prevented perfect copying of unknown quantum states. This limitation initially seemed like a disadvantage, but physicists learned to exploit it for creating communication systems with security properties that were impossible to achieve through classical means. The no-cloning theorem also revealed something profound about the nature of quantum measurement and observation. Every quantum measurement necessarily disturbed the system being observed, extracting some information while destroying other aspects of the quantum state. This trade-off between gaining knowledge and disturbing the system being studied represented a fundamental feature of quantum reality rather than a limitation of measurement technology. Nature itself enforced limits on simultaneous knowledge that no amount of technological sophistication could overcome. These quantum limitations on measurement and information processing began to reshape scientific understanding of knowledge itself. Classical science had assumed that sufficiently precise instruments could eventually measure any property of physical systems without fundamentally altering those systems. But quantum mechanics revealed that the act of measurement always involved an irreversible interaction between the measuring device and the system being measured, making perfect knowledge impossible in principle rather than merely difficult in practice. The implications of quantum measurement limitations extended far beyond laboratory physics into questions about the nature of scientific knowledge and objective reality. If every measurement necessarily disturbed the system being observed, then the classical ideal of detached objective observation became impossible to achieve. Scientists could never stand completely outside the systems they studied, but always participated in creating the phenomena they observed through their choice of measurement procedures. This participatory aspect of quantum measurement suggested that the boundary between observer and observed was far more fluid than classical science had assumed. The properties that scientists detected in quantum systems depended fundamentally on how they chose to look for those properties, with different measurement approaches revealing different aspects of quantum reality. The universe seemed to respond to questions posed by conscious observers, providing questions were formulated. The role answers that reflected the specific ways those of consciousness in quantum mechanics remained one of the most controversial and poorly understood aspects of the quantum revolution. Some physicists argued that conscious observation played a fundamental role in causing the collapse of quantum superpositions into definite classical outcomes. According to this view, the universe existed in ghostly superposition states until conscious beings forced it to choose definite realities through their observations and measurements. Other researchers rejected the special role of consciousness in quantum mechanics, arguing that any sufficiently complex interaction could cause the collapse of quantum superpositions without requiring conscious observation. They proposed that the classical world emerged through environmental decoherence, where interactions with the surrounding environment gradually destroyed quantum coherence and created the appearance of definite classical properties. The debate over consciousness and quantum measurement intersected with deeper questions about the nature of mind and its relationship to physical reality. If consciousness really did play a fundamental role in quantum mechanics, then the traditional scientific assumption that mind emerged from matter would need to be reconsidered. Instead, consciousness might represent a basic feature of the universe that participated in the creation of physical reality rather than simply observing it from the outside. These questions about consciousness and quantum mechanics gained additional urgency as physicists began discovering quantum effects in biological systems that seemed impossible according to classical understanding of living organisms. Photosynthesis, the process that powers most life on Earth, appeared to exploit quantum coherence to achieve energy transfer efficiencies that approached theoretical limits. Plants had somehow learned to maintain quantum superposition states in warm, wet cellular environments that should have destroyed quantum effects almost instantaneously. The discovery of quantum effects in photosynthesis suggested that evolution had been experimenting with quantum information processing for billions of years before humans discovered quantum mechanics. Natural selection seemed to have found ways to protect and exploit quantum coherence for biological advantage, indicating that the boundary between quantum and classical physics was more subtle and context-dependent than physicists had realized. Bird navigation systems provided another example of quantum effects in biological contexts, with specialized proteins apparently using quantum entanglement to detect Earth's magnetic field with extraordinary sensitivity. These biological quantum sensors operated in environments that seemed completely hostile to quantum coherence, yet somehow maintained the delicate quantum correlations necessary for their function. The existence of quantum biology raised profound questions about the relationship between life and quantum mechanics. If living systems could harness quantum effects for essential biological functions, then life itself might represent a particular form of quantum information processing that emerged when matter organized itself into sufficiently complex patterns. The emergence of life from non-living matter could correspond to the spontaneous organization of quantum information processing capabilities in molecular networks. This quantum view of life suggested that the traditional distinction between living and non-living matter might be less fundamental than previously assumed. Instead of representing a sharp boundary, the transition from non-life to life could involve the gradual emergence of increasingly sophisticated quantum information processing capabilities in molecular systems. Consciousness itself might represent the ultimate expression of this quantum information processing, arising when biological networks achieved sufficient complexity to model themselves and their environment. The implications of quantum biology for understanding consciousness and the nature of mind remained highly speculative but deeply intriguing. If biological systems could maintain quantum coherence in cellular environments, then neural networks might exploit quantum effects for information processing capabilities that transcended classical computational limits. The human brain might operate as a quantum computer that used superposition and entanglement to process information in ways that classical neural network models couldn't explain. Some researchers propose that quantum effects in neural microtubules or other cellular structures could account for the subjective experience of consciousness and the apparent unity of conscious awareness. According to these theories, the stream of consciousness corresponded to the ongoing collapse of quantum superpositions in neural networks, with each moment of awareness representing the selection of definite outcomes from quantum possibilities. These quantum theories of consciousness faced significant skepticism from neuroscientists and physicists who argued that the brain operated as a classical system where quantum effects would be rapidly destroyed by thermal noise and environmental decoherence. They pointed out that maintaining quantum coherence required extraordinary isolation from environmental disturbances, conditions that seemed incompatible with the warm, electrically active environment of neural tissue. Supporters of quantum consciousness theories countered that biological systems had demonstrated remarkable abilities to maintain quantum coherence under seemingly impossible conditions, suggesting that evolution might have developed protective mechanisms that could preserve quantum effects even in neural environments. They argued that dismissing quantum effects in the brain based on classical assumptions about decoherence might overlook sophisticated biological strategies for quantum information processing. The debate over quantum consciousness reflected broader uncertainties about the boundary between quantum and classical physics in complex systems, while the mathematical formalism of quantum mechanics provided precise predictions for simple laboratory systems. Extending quantum descriptions to macroscopic objects like biological organisms remained extraordinarily challenging. The transition from quantum to classical behavior involved decoherence processes that were difficult to calculate exactly for realistic systems. These computational challenges meant that many questions about quantum effects in biological and technological systems remained open to experimental investigation rather than theoretical resolution. Researchers began developing increasingly sophisticated techniques for detecting and manipulating quantum coherence in complex environments, pushing the boundaries of what was possible in terms of maintaining quantum effects under realistic conditions. The practical applications of these advances in quantum control began to emerge in technologies that exploited quantum effects for capabilities that classical systems could never achieve. Quantum computers demonstrated computational advantages for specific problems by using superposition and entanglement to explore solution spaces that were exponentially larger than what classical computers could handle. These quantum computational capabilities suggested that natural systems might employ similar quantum information processing strategies for solving complex optimization problems. Quantum sensing technologies achieved measurement precisions that approached fundamental limits imposed by quantum mechanics itself, enabling detection of gravitational waves, magnetic fields, and other physical quantities with sensitivities that exceeded classical instruments by orders of magnitude. These quantum sensors revealed that the quantum properties that seemed like exotic curiosities in laboratory experiments could be harnessed for practical applications with transformative potential. The success of quantum technologies in achieving capabilities beyond classical limits provided compelling evidence that quantum mechanics represented more than just a theoretical framework for understanding microscopic phenomena. The quantum principles discovered through studying blackbody radiation had become practical tools for manipulating matter, energy, and information in ways that were revolutionizing multiple fields of science and technology. As quantum technologies matured from laboratory demonstrations into commercial applications, they began to reveal new aspects of quantum mechanics that hadn't been apparent from purely theoretical studies. The engineering challenges involved in building practical quantum devices forced physicists to develop deeper understanding of how quantum systems behaved under realistic conditions, leading to discoveries that enriched the theoretical foundations of quantum mechanics. The feedback between quantum technology development and fundamental physics research created a virtuous cycle where practical applications drove theoretical advances, which in turn enabled new technological capabilities. This interplay between theory and application demonstrated that quantum mechanics wasn't simply an abstract mathematical framework, but a practical guide for understanding and manipulating the fundamental processes that governed all natural phenomena. The quantum revolution that began with Planck's reluctant hypothesis about energy quantization had evolved into a comprehensive transformation of human understanding and technological capability, from the discrete energy packets that explained thermal radiation to quantum computers that could solve previously impossible problems. The quantum worldview had proven its power to reveal hidden aspects of reality and enable capabilities that transcended classical limitations. Yet despite decades of experimental confirmations and technological successes, the quantum world continued to surprise researchers with phenomena that challenged even sophisticated quantum theories. Each new discovery revealed additional layers of complexity and strangeness that pushed the boundaries of human understanding further into territories that seemed to transcend ordinary logic and causation. The mathematical precision of quantum mechanical predictions provided powerful tools for making accurate forecasts about experimental outcomes, but the meaning of these mathematical relationships remained as mysterious and counterintuitive as when Planck first proposed them. The quantum description of nature forced physicists to accept that reality operated according to principles that fundamentally challenged human intuitions about causality, locality, and objective existence. This tension between mathematical success and conceptual mystery reflected a deeper truth about the nature of scientific progress and human knowledge. The most profound discoveries often revealed the limitations of human reasoning and forced scientists to develop new ways of thinking that transcended classical categories and assumptions. The quantum revolution had become more than a scientific theory. It represented a fundamental shift in how humans related to the natural world and their place within it. The journey from Planck's energy packets to modern quantum technologies illustrated how scientific revolutions unfold through pathways that their initiators could never have anticipated. What began as a desperate attempt to fix a broken equation about thermal radiation had grown into a comprehensive framework for understanding the deepest aspects of existence, consciousness, and the nature of reality itself. The quantum principles that emerged from studying blackbody radiation continued to drive scientific progress in directions that pushed the boundaries of human knowledge toward questions that had traditionally belonged to philosophy and theology. The quantum mechanical description of nature had become a gateway to exploring the most fundamental mysteries of existence, providing tools for probing the relationships between mind and matter, between determinism and freedom, between individual identity and universal connection. As the quantum revolution continued to unfold in the 21st century, it promised to transform human civilization in ways that would have seemed impossible to previous generations. The same strange principles that had troubled Planck and his contemporaries were becoming the foundation for technologies that could reshape every aspect of human experience, from computation and communication to sensing and simulation. The quantum fabric of reality continued to reveal new patterns and possibilities with each passing discovery, demonstrating that the universe operated according to principles far more wonderful and mysterious than classical physics could ever have suggested. The mathematical elegance of quantum mechanics provided a framework for understanding these phenomena, but the deeper meaning of quantum reality remained an open question that challenged the boundaries of human comprehension. The story of quantum mechanics served as a powerful reminder that the most revolutionary insights often emerged from attempts to solve apparently mundane problems. Planck's investigation of thermal radiation had uncovered principles that would eventually transform human understanding of reality at the most fundamental level, suggesting that other revolutionary discoveries might be hiding behind seemingly ordinary phenomena that current science struggled to explain. Looking toward the future, the quantum revolution showed no signs of reaching completion. Each new experimental breakthrough revealed additional phenomena that challenged existing theories and opened new directions for research. The quantum world continued to surprise even expert physicists with behaviors that transcended classical expectations, indicating that the deepest secrets of quantum reality remained largely unexplored. The principles that Planck had reluctantly introduced to explain how hot objects glow had grown into a comprehensive framework for understanding existence as quantum information processing occurring at scales and speeds beyond human perception. Every phenomenon, from the behavior of subatomic particles to the evolution of cosmic structures, could potentially be understood as manifestations of quantum computational processes that operated according to mathematical laws of extraordinary beauty and precision. Yet the quantum universe revealed through these mathematical descriptions remained fundamentally mysterious, operating according to principles that challenged every assumption about the nature of existence, causality, and knowledge. The quantum revolution had forced humanity to embrace uncertainty and mystery as fundamental features of reality rather than problems to be solved, opening doorways to understanding that transcended classical reasoning and intuition. The quantum mechanical worldview that emerged from Planck's accidental discovery continued to transform how humans understood their place in a universe far stranger, more interconnected, and more wonderful than everyday experience could possibly convey. The quantum fabric of reality stretched beyond the boundaries of space and time, revealing patterns of connection and meaning that suggested existence itself might be far more mysterious and beautiful than any previous generation had dared to imagine. The quantum realm was preparing to unveil its most extraordinary secret, one that would make every previous discovery seem like a gentle introduction to the true nature of reality. As physicists pushed deeper into the mathematical foundations of quantum mechanics, they began to encounter phenomena so bizarre that the human language itself proved inadequate to describe them. The universe wasn't just stranger than they had imagined, it was revealing itself to be stranger than they could imagine. In the 1950s, a brilliant physicist named Hugh Everett III proposed an interpretation of quantum mechanics so radical that it would fundamentally challenge every assumption about existence itself. Everett suggested that when quantum systems appeared to collapse from superposition states into definite outcomes, they didn't actually collapse at all. Instead, every possible outcome occurred simultaneously in parallel branches of reality. Each quantum measurement split the universe into multiple versions, creating an infinite proliferation of parallel worlds where every possible quantum event played out in separate cosmic theaters. This many worlds interpretation meant that every decision you've ever made, every quantum event that has ever occurred, and every possible outcome that could have happened actually did happen somewhere in the vast multiverse of parallel realities. There exists a branch of reality where dinosaurs never went extinct, where you chose a completely different career path, where quantum mechanics was never discovered, and where the laws of physics themselves operate according to alternative principles. The version of you reading these words represents just one strand in an infinite web of parallel selves, each convinced that their reality is the only true one. The mathematical implications of the many worlds interpretation were staggering. If every quantum event created new branches of reality, then the number of parallel universes was increasing at an incomprehensible rate. Every femtosecond, every quantum interaction in every atom throughout the observable universe spawned countless new branches of existence. The multiverse wasn't just large. It was growing exponentially larger with each passing moment, creating an infinity of infinities that expanded beyond any conceivable boundary. Yet, this exponential proliferation of parallel worlds solved several fundamental problems that had plagued quantum mechanics since its inception. The measurement problem disappeared because quantum superpositions never actually collapsed. They simply evolved into entangled states where different branches of reality contained different outcomes. The role of consciousness became irrelevant because every possible observation occurred somewhere in the multiverse, regardless of whether conscious beings witnessed them. The many worlds interpretation also resolved the apparent randomness of quantum mechanics by revealing it to be an artifact of limited perspective. From within any single branch of reality, quantum outcomes appeared random because observers could only experience one outcome from the vast array of possibilities that actually occurred. But from the perspective of the entire multiverse, quantum mechanics was completely deterministic. Every possibility was realized with mathematical precision according to the laws of quantum evolution. This resolution of quantum randomness came at the cost of accepting an almost incomprehensibly vast multiverse, where every horror and every triumph that could possibly occur actually did occur somewhere. In some branches of reality, nuclear wars had destroyed civilization. In others, humanity had achieved technological transcendence and spread throughout the galaxy. Every conceivable variation of history, every possible permutation of physical laws, every imaginable arrangement of matter and energy existed simultaneously in the infinite library of parallel worlds. The ethical implications of the many worlds interpretation proved deeply disturbing to many physicists and philosophers. If every possible action occurred somewhere in the multiverse, then moral choices seemed to lose their significance. Why strive to prevent suffering or promote happiness if every possible outcome happened anyway in some branch of reality? The multiverse appeared to render human agency meaningless by guaranteeing that every choice and its opposite would be realized simultaneously. Supporters of the many worlds interpretation countered that moral responsibility remained meaningful within each branch of reality, even if all possible outcomes occurred somewhere in the multiverse. The version of you making choices in this reality bore responsibility for the consequences of those choices within this branch, regardless of what parallel versions might be doing in alternative worlds. Ethics became a local phenomenon that maintained its importance within individual branches of the infinite cosmic tree. The practical implications of parallel worlds remained largely speculative, but some physicists began exploring whether information or energy could somehow be transferred between different branches of the multiverse. If communication across parallel worlds became possible, it would revolutionize human understanding of identity, causality, and the nature of existence itself. The boundaries between separate realities might prove more permeable than the many worlds interpretation initially suggested. Quantum computers provided tantalizing hints that parallel world effects might already be occurring in carefully controlled laboratory environments. When quantum computers solved certain problems, they appeared to explore solution spaces that contained more possibilities than could fit within our single branch of reality. Some researchers speculated that quantum computers were actually consulting parallel versions of themselves across multiple branches of the multiverse. borrowing computational resources from alternative realities to solve problems in our world. These speculations about multiverse computation led to even more exotic possibilities for future quantum technologies. If parallel worlds could be accessed for computational purposes, then the processing power available to advanced civilizations would be virtually unlimited. Problems that would require longer than the age of the universe to solve using classical computers might become trivial if quantum computers could exploit the computational resources of infinite parallel realities. The many worlds interpretation also suggested new approaches to understanding the nature of consciousness and personal identity. If countless versions of yourself existed across parallel realities, then what made your particular stream of consciousness special? Some philosophers proposed that consciousness represented a pathway through the multiverse, with each moment of awareness corresponding to a choice about which branch of reality to experience. Free will might emerge from the ability to influence which parallel world your consciousness inhabited from moment to moment. Alternative interpretations of quantum mechanics offered different perspectives on the nature of reality, but each carried its own unsettling implications. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggested that quantum systems didn't possess definite properties until measurement forced them to choose specific values. This interpretation preserved the central role of observation in quantum mechanics but left the mechanism of quantum collapse mysterious and unexplained. The pilot wave theory, proposed by Louis de Broglie and developed by David Bohm, attempted to restore determinism to quantum mechanics by introducing hidden variables that guided particle behavior according to precise mathematical laws. In this interpretation, particles possess definite positions and velocities at all times, but these properties remained hidden from direct observation. The apparent randomness of quantum mechanics reflected ignorance about these hidden variables rather than fundamental indeterminacy in nature. Each interpretation of quantum mechanics painted a radically different picture of reality's fundamental nature. Some described a universe where observation created reality through conscious choice. Others portrayed a multiverse where every possibility occurred in parallel branches. Still, others suggested that reality operated according to hidden deterministic laws that remained forever beyond human detection. The mathematical formalism of quantum mechanics remained identical across all interpretations, making them impossible to distinguish through experimental tests. This proliferation of interpretations revealed something profound about the relationship between mathematical description and physical understanding. The equations of quantum mechanics provided extraordinarily precise predictions about experimental outcomes, but they offered no unique insight into the underlying nature of reality. Multiple incompatible worldviews could coexist within the same mathematical framework, each internally consistent but utterly different in their implications for existence, causality, and consciousness. The interpretational ambiguity of quantum mechanics forced physicists to confront uncomfortable questions about the nature of scientific knowledge itself. If multiple contradictory theories could make identical predictions about observable phenomena, then what did it mean to understand reality? The traditional goal of science had been to uncover the true nature of the world through careful observation and mathematical analysis. But quantum mechanics suggested that reality might be fundamentally unknowable, hiding behind a veil of mathematical formalism that described behavior without revealing essence. This crisis of understanding became even more acute as physicists began exploring the quantum foundations of space and time themselves. General relativity described gravity as the curvature of space-time caused by mass and energy, but it treated space and time as smooth, continuous fields. Quantum mechanics revealed that energy and matter existed in discrete packets, suggesting that space and time might also be quantized at the smallest scales. The attempt to combine quantum mechanics with general relativity led to theories of quantum gravity that pushed mathematical physics to its absolute limits. String theory proposed that the fundamental constituents of reality were tiny vibrating strings rather than point particles, with different vibration patterns corresponding to different particles and forces. These strings existed in higher dimensional spaces that remained hidden from direct observation, curled up so small that they couldn't be detected by any conceivable experiment. Loop quantum gravity took a different approach, suggesting that space itself was quantized into discrete units connected in networks that gave rise to smooth geometry at larger scales. In this theory, the familiar three-dimensional space we inhabit emerged from underlying quantum structures that operated according to principles bearing no resemblance to classical geometry. Space and time became emergent phenomena arising from more fundamental quantum informational processes. Both approaches to quantum gravity suggested that the familiar world of objects moving through space and time represented a low-energy approximation of deeper quantum realities. The smooth space-time described by Einstein's equations might be similar to how a calm ocean surface conceals the chaotic molecular motion underneath. Reality, at the most fundamental level, could be utterly alien to human experience, following principles that transcended ordinary concepts of space, time, matter, and causality. The possibility that space and time were emergent rather than fundamental opened doorways to understanding phenomena that had puzzled physicists for decades. Black holes, regions of space-time where gravity became so strong that nothing could escape, might represent windows into the underlying quantum structure of reality. The information that fell into black holes might not be destroyed, but rather encoded in quantum structures that existed beyond ordinary space-time. The holographic principle that emerged from black hole physics suggested that all the information contained in any volume of space could be encoded on the boundary surface of that region. This principle implied that our three-dimensional reality might be a projection of information processing occurring in two dimensions, similar to how a hologram creates three-dimensional images from information stored on flat surfaces. If the holographic principle applied to the entire universe, then everything we experienced as solid reality might be the output of computational processes occurring on a distant cosmic boundary. These holographic theories of reality suggested that the universe operated more like a vast information processing system than a collection of material objects interacting through forces. Every particle, every field, every aspect of physical reality might represent different facets of underlying computational processes that transformed information according to quantum mechanical rules. The laws of physics wouldn't be fundamental principles governing matter and energy, but rather algorithms that determined how information flowed through quantum networks spanning the cosmos. The information theoretic view of reality gained additional support from developments in quantum field theory that revealed the vacuum of empty space to be far from empty. The quantum vacuum seethed with virtual particles that constantly appeared and disappeared, carrying out computations that influenced how real particles behaved when they interacted. These vacuum fluctuations contained virtually unlimited amounts of quantum information that participated in every physical process throughout the universe. The energy density of quantum vacuum fluctuations posed one of the most serious problems in theoretical physics. Naive calculations suggested that empty space should contain enough energy to curve the universe into a tiny ball much smaller than an atomic nucleus. The fact that space appeared flat rather than violently curved indicated that some mechanism was canceling out most of the vacuum energy, but physicists had no idea what that mechanism might be. This cosmological constant problem represented a discrepancy between theory and observation that exceeded a factor of 10 to the 120 power, making it the worst prediction in the history of science. The resolution of the cosmological constant problem might require completely new approaches to understanding the relationship between quantum mechanics and gravity. Some physicists proposed that the vacuum energy was cancelled by contributions from parallel universes in the multiverse, with quantum fluctuations in different branches of reality interfering destructively to produce the nearly zero vacuum energy we observe. Others suggested that the vacuum energy problem indicated fundamental flaws in current approaches to quantum gravity that would require revolutionary new principles to resolve. The search for a theory of quantum gravity became increasingly urgent as experimental evidence accumulated that space and time exhibited quantum properties under extreme conditions. Gravitational wave detectors like LIGO had begun observing ripples in spacetime caused by colliding black holes and neutron stars, providing direct evidence that gravity propagated as waves through the fabric of space and time. These gravitational waves carried information about some of the most violent events in the universe, revealing details about how matter and energy behaved under conditions that pushed the laws of physics to their breaking points. The detection of gravitational waves opened new windows for observing quantum effects in gravitational systems. Future gravitational wave observatories might be sensitive enough to detect quantum fluctuations in spacetime itself, providing direct evidence for the quantization of gravity. These observations could distinguish between different approaches to quantum gravity and reveal which mathematical frameworks correctly describe the quantum nature of space and time. Even more exotic possibilities emerged from theories that treated consciousness as a fundamental feature of quantum reality. If awareness represented a particular type of quantum information processing, then advanced quantum technologies might enable forms of cognitive enhancement that transcended the limitations of biological neural networks. Human consciousness might be augmented through direct interfaces with quantum computers, allowing minds to process information using superposition and entanglement in ways that exceeded any classical computational capability. The potential for quantum enhancement of consciousness raised profound questions about the future of human nature and identity. If cognitive abilities could be expanded through quantum technologies, then the boundary between human and artificial intelligence might dissolve as both forms of awareness began exploiting similar quantum information processing principles. Enhanced humans might develop forms of consciousness that were as different from current human awareness as human consciousness was from that of simpler organisms. These speculations about quantum consciousness and cognitive enhancement remained highly controversial and largely theoretical. The mechanisms by which quantum effects might influence neural information processing were poorly understood, and many researchers remained skeptical that the warm, noisy environment of the brain could support the delicate quantum correlations required for quantum computation. Nevertheless, the rapid progress in quantum technology development suggested that these questions would eventually be resolved through experimental investigation rather than theoretical argument. The practical applications of quantum technologies continued expanding into domains that seemed far removed from the fundamental physics that inspired their development. Quantum sensors achieved measurement sensitivities that approached the limits imposed by quantum uncertainty itself, enabling detection of gravitational waves, magnetic fields, and electric fields with precisions that exceeded classical instruments by many orders of magnitude. These ultra-sensitive quantum sensors found applications ranging from medical imaging and geological surveying to navigation systems that operated independently of GPS satellites. Quantum communication networks began demonstrating secure information transfer over intercontinental distances using quantum key distribution protocols that exploited the fundamental properties of quantum mechanics to detect eavesdropping attempts. Any effort to intercept quantum encrypted messages would necessarily disturb the quantum states being transmitted, alerting the legitimate users to the security breach. This quantum cryptography provided security guarantees that depended on the laws of physics rather than mathematical complexity, making it theoretically unbreakable even by adversaries with unlimited computational resources. The development of quantum internet protocols promised to extend quantum communication capabilities to global scales, creating networks where quantum computers could share entangled states and quantum information across arbitrary distances. These quantum networks might enable distributed quantum computing architectures where the processing power of multiple quantum computers could be combined to solve problems that exceeded the capabilities of any individual machine. The integration of quantum technologies with classical information systems began creating hybrid architectures that exploited the unique advantages of both quantum and classical computation. Quantum computers excelled at certain types of optimization and simulation problems, but remained inferior to classical computers for most conventional computational tasks. The most powerful future computing systems would likely combine quantum and classical processors in architectures that automatically allocated different types of problems to the most appropriate computational resources. As quantum technologies matured from laboratory demonstrations into commercial applications, they began revealing aspects of quantum mechanics that hadn't been apparent from purely theoretical studies. The engineering challenges involved in building practical quantum devices forced researchers to develop deeper understanding of how quantum systems behaved under realistic conditions, leading to discoveries that enriched the theoretical foundations of quantum mechanics while enabling new technological capabilities. The feedback between quantum technology development and fundamental physics research created a virtuous cycle where practical applications drove theoretical advances, which in turn enabled even more sophisticated technologies. This interplay between theory and application demonstrated that quantum mechanics wasn't simply an abstract mathematical framework for understanding microscopic phenomena, but a practical guide for manipulating matter, energy, and information at the most fundamental level. The quantum revolution that began with Planck's reluctant hypothesis about energy quantization had evolved far beyond anything its founders could have imagined. The discrete energy packets that emerged from studying thermal radiation had grown into a comprehensive framework for understanding reality as quantum information processing, occurring at scales ranging from subatomic particles to cosmic structures. Every aspect of existence, from the behavior of individual atoms to the evolution of entire galaxies, could potentially be understood as manifestations of quantum computational processes operating according to mathematical principles of extraordinary elegance and power. Yet despite decades of experimental confirmations and technological breakthroughs, the quantum world continued to surprise researchers with phenomena that challenged even the most sophisticated theories. Each new discovery revealed additional layers of complexity and mystery that pushed the boundaries of human understanding further into territories that seemed to transcend ordinary logic and causation. The mathematical precision of quantum mechanical predictions provided powerful tools for forecasting experimental outcomes and designing revolutionary technologies. But the deeper meaning of these mathematical relationships remained as enigmatic as when Planck first proposed them over a century ago. This persistent mystery at the heart of quantum mechanics reflected something profound about the nature of scientific knowledge and human understanding. The most fundamental aspects of reality often revealed themselves through mathematical descriptions that exceeded the capacity of human intuition to visualize or comprehend. The quantum description of nature forced scientists to accept that existence operated according to principles that fundamentally transcended classical concepts of objects, properties, and causal relationships. The quantum mechanical worldview represented more than just a scientific theory about the behavior of matter and energy. It had become a new way of understanding humanity's relationship to the natural world and our place within the cosmic order. The quantum universe revealed itself as a realm where observation and reality were inseparably intertwined, where individual systems participated in networks of connection that spanned arbitrary distances, and where the act of measurement helped create the phenomena being observed. The transformation from classical to quantum thinking required abandoning comfortable assumptions about determinism, locality, and objective reality in favor of probabilistic descriptions that emphasized relationship and process over substance and structure. This shift represented a fundamental change in how humans understood their role as observers and participants in the cosmic drama rather than detached spectators watching events unfold according to predetermined laws. The quantum principles that emerged from Planck's investigation of thermal radiation continued driving scientific progress toward questions that probe the deepest mysteries of existence, consciousness, and meaning. The mathematical framework of quantum mechanics had become a gateway for exploring the boundaries between physics and philosophy, between determinism and freedom, between individual identity and universal connection. These explorations revealed that the quantum revolution extended far beyond the domain of physics into fundamental questions about the nature of knowledge, reality, and human experience. As the 21st century progressed, quantum technologies began demonstrating capabilities that would have seemed impossible to previous generations. Quantum computers solved certain problems by apparently consulting parallel universes. Quantum sensors detected phenomena that operated at the very limits of physical possibility. Quantum communication systems achieved security guarantees that depended on the fundamental structure of reality itself. These remarkable achievements provided compelling evidence that the strange principles of quantum mechanics represented practical tools for understanding and manipulating the deepest aspects of natural phenomena. The success of quantum technologies also demonstrated that the bizarre behaviors observed in laboratory experiments reflected genuine features of reality rather than mere mathematical curiosities. The quantum effects that had seemed like exotic anomalies when first discovered were proving to be fundamental aspects of how the universe operated at every scale and in every context. The classical world of everyday experience was revealing itself to be a limited approximation of underlying quantum realities that operated according to principles far stranger and more wonderful than human intuition could grasp. The ongoing quantum revolution showed no signs of reaching completion. Each new experimental breakthrough revealed additional phenomena that challenged existing theories and opened new directions for research. The quantum realm continued to surprise even expert physicists with behaviors that transcended classical expectations, indicating that the deepest secrets of quantum reality remained largely unexplored. The mathematical tools developed for describing quantum phenomena provided frameworks for understanding these discoveries, but the ultimate meaning of quantum mechanics remained an open question that challenged the boundaries of human comprehension. The journey from Planck's energy packets to modern quantum technologies illustrated how scientific revolutions unfold through pathways that their initiators could never have anticipated. What began as a desperate attempt to resolve a mathematical inconsistency in thermal radiation theory had grown into a comprehensive transformation of human understanding about the fundamental nature of existence. The quantum mechanical description of reality had become both the most precisely tested theory in the history of science and the most mysterious, providing unparalleled predictive power while remaining fundamentally enigmatic in its deeper implications. From Max Planck's reluctant mathematical desperate fix to the quantum computers reshaping our world today, we've witnessed how one man's attempt to solve a simple problem about glowing objects accidentally unlocked the deepest secrets of reality itself. The discrete energy packets he introduced to save classical physics became the foundation for understanding existence as quantum information processing occurring at scales beyond human perception. Every breakthrough revealed layers of strangeness that challenged our most basic assumptions about causality, locality, and the nature of observation. The quantum fabric of reality continues surprising us with each discovery, reminding us that the universe operates according to principles far more mysterious and interconnected than our everyday experience suggests. Who knows what revolutionary insights await in the seemingly ordinary problems that today's scientists struggle to solve?